Alright, we're going to go ahead and take a look at this example from the previous video. A hot air balloon is rising straight upward with a constant speed of 6.5 meters per second. When the basket of the balloon is 20.0 meters above the ground, a bag of sand tied to the basket comes loose. How long is the bag of sand in the air before it hits the ground? So anytime we have a problem involving motion that goes up and down, there are two different ways of doing this. My recommendation would be to separate the problem into an up part, the motion going up, and then the motion going down. So let's go ahead and take a look at just the motion going up. We're trying to find the total time of going up and down, but we don't know the time going up. We know that the balloon or the basket is moving at 6.5 meters per second upwards, the sandbag I should say. Let's call our up direction positive in this case. We know that when it stops, the final velocity is going to be 0 meters per second. We also know the acceleration is still going to be negative 9.8 meters per second squared. So we can use this equation Vf equals Vi plus At. It contains all the variables we need to solve for time. So 0 equals 6.5 plus negative 9.8 t. Negative 6.5 equals negative 9.8 t. So therefore t equals 0.663 seconds when you do it on your calculator. That's the time it takes to go up. To find the time it takes to go down, we're probably going to need more pieces of information. We know the initial velocity going down is 0 meters per second. We don't know the final velocity it's going to reach because now it has to go down further than when it was launched. We also, because of that, don't know the displacement yet. All we know right now is the acceleration, which is still negative 9.8 meters per second. Let's go ahead and erase this. We want to keep our t up there. Alright, so to find that distance going down, we know it was at 20 meters as it was going up. So at 20 meters, it then went up for another 0.63 seconds at that acceleration. So let's find our displacement in that time, knowing the acceleration. So delta x equals VIT plus 1/2 AT squared. Delta x is my initial velocity, which was, again, 6.5 meters per second, times t, which is 0.663, I got that from here, plus 1/2 times negative 9.8 times t again, squared. Go ahead and erase this now. Okay, so if we solve this on a calculator, you should get 4.3 plus negative 2.15. That correctly. So 4.3 minus 2.15 should give us a displacement, meaning it went up 2.15 meters beyond the 20 meters. So the total height it went up, and also the total height it's going to be coming down, looks like it's going to be 20 meters plus 2.15 meters, or 22.2 meters roughly. So keep that in mind, that 22.2 meters. We also know the time it took to go up was 0.663 seconds. These are two key pieces of information as we move forward. So we know the up displacement was 22.2 meters. We know the up time was 0.663 seconds. Now working with down, to find the time, we also know that it's going to go down a negative. The displacement in a negative direction would be 22.2 meters going down. We know the final velocity would be 0 meters per second. We know the acceleration stays constant at negative 9.8 meters per second squared. We also know my initial velocity at the top of its path. It started moving down at 0 meters per second. No. I misstated my final velocity up here. Initial velocity is what actually equals 0 meters per second as it's traveling down. Final velocity we don't know yet, but that's okay, because we can use delta x equals VIT plus 1/2 AT squared. This term turns to 0 because my initial velocity is 0. Delta x is negative 22.2 times negative 9.8 t squared. Solve for t squared. I get 4.53. So then my time coming down ends up being 2.13 seconds. Now remember, it went up 4.663, so let's add those two times together. 0.663 and 2.13. We're going to end up with 2.8 with our sig figures seconds. So that's how we got the amount of time it was in the air. We also actually found the greatest height already. We know that the greatest height was at 22.2 meters, but let's make it 22 to keep our sig figs consistent. So our greatest height was 22 meters. Our time was 2.8 seconds. Notice you're not always going to solve these in order. They're asked if you come up with your own method. That's the beauty of these kinematic equations. There's multiple ways of doing it. If you understand this method and it's sufficient for you, great. You don't need to watch my solving it the second way, but just know that I would like you to try this problem here that I just showed you the answer to. But what is the velocity of the bag of sand just before it hits the ground? That's kind of continuing on with what we were working on. The answer you should get is negative 21 meters per second, or 21 meters per second downward. And then in conclusion, just go ahead and read the free fall rides section on page 74-75. Try the challenge problem on page 75. And again, that's all I need if you understand how we worked through that previous problem, but I do want to show you another way of solving it. Just let me clear my invitations. Alright, so another way we could have looked at this. We know our delta x is equal to VIT plus 1/2 AT squared, or in other words, my change in position is VIT plus 1/2 AT squared. I just made this delta x my change in position, xf minus xi. we can solve this for t. Well, actually, first, what I want to do is take a t out. So x sub f minus x sub I equals t times vi plus 1/2 at.